Welcome to this explainer. You know, it's wild to think about, but the modern computer wasn't just born in some sudden single eureka moment. Instead, it actually emerged from a grueling 30-year relay race of innovation. Today, we're going to trace this incredible race, one that was driven by mathematicians, engineers, and governments, all chasing a prize that wasn't just about building a faster calculator, but creating a machine truly capable of human reasoning. So let's jump right in with a question that kind of shatters a very common modern assumption we all have. If I ask you right now where the very first computer was built, what instantly pops into your head? If you're like most of us, your brain probably jumps straight to, sleek Silicon Valley tech campuses, or maybe some guy in a hoodie typing away on a laptop. But the reality? Oh, it couldn't be more different. The very first computers were these enormous, power-hungry beasts that physically occupied entire rooms. And the people building them at the time had absolutely no idea they were laying the groundwork for the modern world we live in today.
All right, Section 1. The first giant machines. Math before machines.
You see, before any engineer could even think about soldering a wire, mathematicians actually had to prove that computing was theoretically possible in the first place. Back in 1936, Alan Turing established a really profound concept. It was a purely mathematical, theoretical machine that can manipulate symbols based on a specific set of rules. He basically proved that a machine could, in principle, perform general computations if you just gave it the right instructions. It wasn't physical yet, but this idea, it became the absolute bedrock of all computer science.
Moving into Section 2. War and vacuum tubes. The wartime catalyst.
So when World War II broke out, all that theoretical math suddenly became a literal matter of life and death. Governments found themselves absolutely drowning in massive calculations. We're talking ballistic trajectories, complex cryptography, aircraft design, weapons research. Human brains and human hands were just way too slow to handle the staggering scale of these urgent wartime problems. And it was exactly this urgent need that led to the first practical, though absolutely massive, electronic solutions. Over in Britain, you had Colossus, which was this electromechanical marvel used for analyzing encrypted German communications. Then across the Atlantic in 1945, the University of Pennsylvania completed ENIAC. Packed with literally thousands of glowing vacuum tubes, ENIAC was a true general-purpose computer. Sure, it was a complete energy hog, but electronic computation had finally become a physical reality. Now, ENIAC's massive advantage was obviously its speed. It absolutely destroyed human calculation times. But it had a glaring limitation that was honestly just a total nightmare. Programming it wasn't like typing on a keyboard today. It meant operators had to physically plug in the thick cables and flip these heavy switches. You were literally rewiring a room-sized machine every single time you wanted it to do something new.
The elegant solution to that physical bottleneck? Well, it actually became the central architecture for literally every device we use today, the stored program. The realization they had was brilliant. Instead of physically rewiring the hardware every time, why not just store the instructions in the computer's memory and change them electronically?
Which brings us to Section 3, the miniaturization revolution, shrinking the giant. Because look, even with better programming, the physical hardware was still a massive liability. Vacuum tubes were incredibly fragile, they generated terrible heat, and when you have thousands of them crammed into one room, things are constantly going to break. Enter Bell Labs in 1947. John Bardeen, Walter Brattain, and William Shockley invented the transistor. It did the exact same job as the vacuum tube, but it was tiny, it was highly reliable, and it ran cool. Computing was finally ready to shrink. Fast forward a bit to the 1950s, and engineers took this a massive step further with the integrated circuit. Instead of hand-wiring individual transistors together one by one, they figured out how to bake multiple electronic components onto a single piece of semiconductor material. The physical footprint shrank dramatically, complexity just skyrocketed, and costs plummeted. And man, this miniaturization could not have come at a better time because NASA was dealing with constraints where human calculation was utterly impossible. During the 1960s, the Apollo program needed a system small and light enough to actually guide a spacecraft all the way to the moon. Every single kilogram mattered. Operating flawlessly under that kind of intense pressure, space exploration proved exactly what miniaturized computing could achieve. Let's head into Section 4. The personal computing boom, the microprocessor. This relentless push to get smaller and smaller hit a massive landmark in the year 1971. That is when Intel introduced the 4004, the world's first commercially available microprocessor. This was completely revolutionary. All the central processing functions of a computer were now crammed onto a single affordable chip. Computing was no longer just locked away in government labs. And that single chip, it completely opened the floodgates in the 70s and 80s. Computing shifted from giant rooms with guys in lab coats to hobbyists and teenagers tinkering away in their garages. Companies like Apple, IBM, and Microsoft really seized the moment, turning what was once an exclusive multi-million-dollar tool into a mass-market household consumer product. When you actually take a step back and look at this rapid timeline, it is truly staggering. In barely 40 years, humanity went from abstract mathematical theories in the 30s to room-sized glowing heaters in the 40s to integrated circuits and finally microprocessors in the 70s. Every single decade literally built upon the hard-fought solutions of the last.
This takes us to Section 5, an ecosystem of inventions, the compounding effect.
And this brings us to probably the most important takeaway of this whole explainer. The computer was never, ever created by a lone genius working in a vacuum. Technological revolutions happen because an entire ecosystem of thousands of people solve thousands of highly specific smaller problems. One team improves memory, another advances the processor, someone else invents new code, and others build the manufacturing techniques. They all interlock until the impossible becomes ordinary. And you know that compounding relay race? It literally never stopped. In the 80s, PCs linked up on local networks. By the 90s, the internet turned these isolated machines into global nodes. Today, smartphones make computing totally mobile, massive cloud servers handle the heavy lifting, and AI is demanding unprecedented processing power. But here's the crazy part. Even as we race toward things like quantum computers and advanced robotics today, the fundamental ambition hasn't really changed since Alan Turing's time. Step 1. Turn information into computation. Step 2, turn that computation into capability. And step 3, turn that capability into something humanity can actually use. The giant machines that once filled entire rooms and just chugged staggering amounts of electricity have become almost invisible to us, slipping into our pockets, navigating our cities, and translating our languages in real time. The race to build the computer didn't end. It just changed form, which leaves us with one incredibly exciting question to think about. As this ecosystem of invention continues to accelerate, what seemingly impossible piece of science fiction will become ordinary next? Thanks for joining me on this explainer, and keep questioning what's possible.